So, okay, so thank you very much for coming. It is my pleasure to introduce Karolina Dziadura, who's a postdoctoral researcher at the Minor Planet Center at the Center for Astrophysics. Her work focuses on asteroid astrometry, orbital dynamics, and the analysis of observational data quality using large-scale data sets. She earned her PhD in astronomy from Adam Mickiewicz University in Poznań in Poland, where she worked on the detection of the Yarkovsky effect using Gaia data. So today she will be telling us about how to use global characterization of the quality of all-sky asteroid astrometry. So we're very happy to have Karolina. This is a very unique topic for the high energy seminar, so take it away.
Hello, thank you everyone for letting me speak about asteroids and the high energy seminar. I hope you can hear me well. Doesn't work. Okay, it works. I want to talk about orbits of asteroids, and the idea of that is that we want to have them the most accurate as we can, because it's very important for many reasons. For example, for planetary defense, like if there is a possible impact, we want to compute the orbit the most accurate as we can. It's also very important for the solar system dynamic. And in order to do that, in order to have accurate orbit, we need to have accurate astrometry. And so far, we have a lot of observatories. It's over 2,000 of them, over 2,000 telescopes that are providing data on a daily basis. They are providing astrometry on a daily basis. And the thing is that we have one object that has various observations from various telescopes, and each observatory has its own pipelines, has its own instruments, and each data is different. And based on this all various data, we want to compute one orbit. So we need to know which data is trustworthy, which data is like a little bit less trustworthy, because the idea would be to better understand the all statistics behind the all data that we have right now. And I will mention in the next slide how much data we have, because then we can better weight the observatories, and because of that we can better predict our orbits, and this is the main goal. But in this presentation I will talk a lot about residuals of observations. So let me just briefly tell you what are they, because maybe some people are not familiar with that. So here's just a very simple representation of the reference frame and right ascension and declination. And on top of that, we have observations, right? Black dots, they represent observations. And for this observation, we fit the orbit. And if the observation is too far from the orbit, it might be rejected. It's only a few are getting rejected. The reason for that might be just some mistake in the data, or sometimes even like sometimes is a mislinking the object. So if the place is very dense in asteroids, sometimes it might be a different asteroid, a different object, and there was a mislinking, but we can see it in data and we reject these observations. Later on, we see residuals. So the difference between actual observation and the orbit that we computed. And these residuals are provided in right ascension and declination. And about these residuals in right ascension and declination, so again, the difference between orbit and the observation, I will talk about a little bit more in a moment. But what affects our residuals? Because I told you that each observatory is different, but we can start from the stellar catalog. So we are doing astrometry. Asteroid astrometry is we are doing it based on the stellar catalogs. So if there's something wrong with a stellar catalog, is there some systematic biases in the stellar catalogs, we will also see it in our astrometry of asteroids. There's also magnitude. There's some specific, it's pretty obvious, there's some specific range of magnitude that observations will be just the most accurate. If it's too bright or if it's too faint, the observation won't be that accurate. Rate of motion, yeah, if the object is near Earth, so it will move a little bit faster. We have some potential trailing and timing errors. Epoch. So again, a little bit about observatories. So they use during time they change the use of a catalog. They adjust the instrument. They adjust their pipeline for astrometry. So we see also how it differs in time. And last, observatory-specific factors. So the telescope type, detector quality, also weather, reduction pipeline, the CCD camera, and features like that also influence our residuals. But speaking of data, so I told you that I'm working on data of astrometry of asteroids, that they are coming from different telescopes. And for now, we have over 1.5 million asteroids detected. But for this study, I chose only over 700,000 of them that have numbers. In order for asteroid to get a number, it has to meet some specific thresholds. So one of them is like its orbit has to be under specific uncertainty, and it has to be observed in a few oppositions. So that's why I know that these observations are trustworthy. That's why they were chosen for this analysis. Even with that, these observations of number of 700, even though they are like half of the population, they are responsible for around 90% of all astrometry that we have right now. So this is like a very big sample of data. And we have different telescopes. So not only asteroids are observed by different surveys, mostly, and these are the most productive surveys that we have right now. So you see Pan-STARRS, you see Catalina. So for example, Pan-STARRS, it has even more than these two telescopes, but these two are the most productive. As well with Catalina, it is even more than these two, but these two are the most productive. Atlas, another super productive survey. And funny is linear because it actually stopped observing in 2013, which is a pretty long time ago, but it still remains one of the most productive observatories. So far, we don't see Vera Rubin yet, but you might see that in 10 hours it observed, like it discovered over 2,000 new near-Earth objects, but it will provide daily data in a couple of months. But let's move on to data by astrometry catalog and telescopes. So I mentioned that we are doing a differential astrometry, which basically means that we are using the stellar catalogs. Here are the list of the stellar catalogs that were ever used in the astrometry. So you see it's a lot of them. It's not only Gaia 2 mass and that's it. It's a lot of them. But the most productive so far is Gaia DR2. So on this axis, you see different observatories that I mentioned before. And Gaia is everywhere. This site, in this one, again, 704, I mentioned that it stopped observing 2013, which just basically they didn't have the chance to use Gaia DR2. And another example, F51, one of the most productive observatory, one of the Pan-STARRS observatories. You see that it used not only one, but like a lot of different stellar catalogs, and I will talk about it in a moment. But so far, Gaia DR2 is the most popular at this moment, and then DR1, UCAC 4E, and others. But in order to present you the idea of statistical analysis of this observatories, I thought that maybe giving you these two examples as a comparison would be great, because on the top you see Pan-STARRS, on the bottom you see Catalina. They are both one of the most productive surveys, but Pan-STARRS is very, very good, and Catalina, we see that it has some small problems. So I feel like it's a nice comparison so for you to understand how telescopes differ. So Pan-STARRS observed since 2008, a 1.8 meter telescope, field of view 7 degrees, while Catalina started, actually it started observing 62, but it was not observing asteroids. Then they switched to the CCD camera, and actually 2003, and another CCD camera to upgrade 2017, which we actually remember that date. We can actually see it in data, and I will mention it later. So on the left panel, you see that fun stars. Here are the residuals. Here's there are the residuals, and there are the number of observations. So we see that the range of residuals, they are the same scale for the comparison. So you see that in right ascension, they are much closer, and here a little bit wider. So it's like on the very first look, we know that fun stars residuals are just smaller and better, and the same for the declination. But this is not what is most important. Most important is if these observations are biased in some direction. So for fun stars, the mean value, which is the red line, is around 0 for right ascension declination. But for Catalina, unfortunately, we have some bias in the mean value. That's why we want to take a closer look at that and see where is this coming from. Is there some specific group of objects that is causing that shift? Specific magnitude, specific catalog that they use that is causing that shift, and this is what was the job. One more fun fact: the F51 fun stars was actually the one that discovered Oumuamua, so the interstellar object. Okay, Catalina, year by year, we'll see here are the residuals, top panel, right ascension, here declination, and we have its observations in years. So we started observing very long time ago, and then I mentioned 2017. We see that the residuals got a little bit smaller. This is the mean value. The orange line is the mean value. So we see that around 2017. So it's not only the reason of switching to the new CCD camera, but also when I divide this plot by catalogs that they use for the reduction, we see that they started with FuseNull, then they move on to UCAC 2, then UCAC 4, and then they switch to Gaia. So again, 2017 is Gaia. So we know that Gaia is basically making these observations better. And the same plot, you see, I will go back, focus on this one. This is Catalina, and again, this is Pan-STARRS. So the scale is the same. So we see that Pan-STARRS just basically, once again, residuals are smaller, but again, there are some small biases especially in the declination, and we are wondering where are they coming from. And when we divide this plot for catalogs, they also started using Gaia around 2017, and we also see it in data that basically we see that residuals got smaller. So another example how Gaia improved our option. Okay. Moving on to magnitude. So we also see now we don't have years here, we have magnitude here. So you see that, as I mentioned, there's some range of magnitude that gives us the smaller residuals. And basically, this is as expected. We can have oversaturation when they are too bright, or too small signal to noise ratio when they are not bright enough. So left panel is for Catalina, right panel is for Pan-STARRS. Another feature that I was looking at was, does it depend on the group of objects that we are observing, because near objects will be moving a little bit faster. But at this level of precision that I just divided them by group, I don't see a huge differences between colors. So like Venus Magnus near Term is blue, and other objects are yellow. So basically, I don't see a huge difference between these groups. So another step would be to look at the rate of motion. So actually, the how fast are these objects? But this will be for the future work. Moving on to these are the plots that I feel like I'm most excited about, because they are not only showing the dependency on the catalog, the stellar catalog that was used for the reduction, also year, and also actually the state position. Because I was wondering does it also depends on the sky position? So maybe there's some specific areas that telescopes are looking on that are that will provide like some biases. There's some offsets in data. So here you have the observational graph. So you see how the telescope was scanning the sky. On the first here you have residuals for all of the catalogs, and then divided by stellar catalogs that were most common used for the reduction from the most popular to the least popular. That's why it's not full. So I hope you can see it. I think you can see it for TUMAS, which was used for pan-stars between 2008 and 2017. We have this different colors features. So we also see that it actually depends for some catalogs. It also depends on the sky position, the mean value or the residuals. We have Gaia. It's a little bit more gray, which is what we want. We want this to be around 0. We want the mean values to be around 0. Here as well, we can see some coloring, but it's like very, very small. And this is for the right ascension. The same for declination for this telescope, very similar. But then we look at Catalina, and it's a little bit intense in colors. What we see, Gaia there too provided a little bit more grayish color, which is great. Then epoch 2, epoch 4 actually has a lot of coloring, especially this one is interesting because see like in this area of the sky, you have definitely shift to negative values, and these areas have the shift for the positive values. So we see that for some stellar catalogs that were used in some years, we also see the sky position dependency. At this point, you might ask, and I was also asking this question to myself and to my supervisors, what are the lines coming from? And it took me some time to find the reason, but yes, it's data truncation or branding. Yeah, it's probably random, but basically I found out the reason for that, but this is not for the orbit computation, this is just for the display of this plot, but I got the data to fix the display last week, so I haven't fixed that. So that's why you see these lines. So basically, I assume if I fix the rounding, the colors will be the same, just without this very specific line here. And here Catalina for declination. So declination is moved into positive values. But the most important to take is like here are the reddish colors around epoch 2, epoch 4, and more grayish, which is again what we want with Gaia. So another reason to use Gaia. But I just wanted to mention here, because I feel like I don't have much more time, but I just want to mention that basically we don't want to only look for most relative catalogs, observatories, but also for all of them. And this is just an example of what we see. Here on this side, you have number of observatories. And at this point, I showed the mean residuals and declination per observatory per magnitude. So you see that in different magnitudes, we have for different telescopes, we have a different mean residuals that actually, like we can see this for all of these telescopes. But you can look at F51 on the top, and it looks pretty good. So this is what we want to do for all of the observatories. And the idea would be to in the end like build the RMS-based rating scheme that will take into account all of these features. So catalog, magnitude here, observatory and sky position, and in order to use this weighting scheme that to compute orbits in a better accuracy, and it has been proven before in many papers that even like a not such a complex weighting scheme, even like a smaller weighting scheme, is still improves our orbit computation and decreases the uncertainties of the orbit. And as I mentioned, this is what we are aiming for, is to compute the orbits of asteroids as accurate as we can. So here are the things that we found, like the residual from the distance on a stellar catalog. So yes, Gaia looks very like the best, but this was to be expected. We see clear magnitude trend even after V-band conversion. I didn't show it here because well, I converted it to the V-band as well, but both were basically the same, so I didn't even mention it here. And some catalogs show sky position dependency patterns, and I think this is interesting to see. I don't see like major at this point, at this level, I don't see the major differences in asteroid groups. There's a clearly yearly dependency offset when for specific observatories, and there are some catalogs like mentioned epoch 2 and epoch 4 that show like this systematic like biases. And the future work will be to also analyze the rate of motion effect, include some part of unnumbered objects to see if the statistics looks the same. And as I mentioned, the bigger picture will be the weighting scheme to improve the orbit fitting and maybe contact some observatories. That's it. Thank you.
Thank you so much for the nice talk and for being on time. Any questions for Karolina from the room or from Zoom?
Hey, Karolina, thank you so much. I have a question on the oversaturation. You showed at the low magnitude and for the bright sources, the positional accuracy increased because the camera is oversaturated.
Oh, no, sorry. This was the, no, this is basically, we want them to be the smallest because they're residual. So this means that they decrease, and this means that they decrease. So decrease in the oversaturation and decrease in when you have a small signal noise ratio. Like sorry, residuals are bigger, basically.
Right. I was wondering whether there are any ways to mitigate that effect, whether there are any technical ways to treat that oversaturation, or if it's just
You mean like
you have to accept that the uncertainties become larger.
you mean like to train pipeline to
Yeah,
figure
for
this out?
example.
I'm sure there are probably the ways to make we do it better, but the idea with about the oversaturation is like you don't know where's the center of the object. So there's like always you don't know how to exactly choose the mass center, right? So
Right, yeah.
but this is not I I never done any pipeline for the observatories for the astrometry.
Thanks.
Thanks. But this is what observatories are doing. So they like it's a observatory-specific pipeline that they are using. It's not like they provide MPC already computed data. Just like the numbers, not raw images.
In the meantime, while I pass the microphone, I also had a very small question. Like, is there any obvious reason why Gaia DR3 is sort of less capable for this exercise than Gaia DR2? Or
You mean this plot?
Yeah, in terms of the impact that they've had in building these catalogs, because like at least for some objects, you would expect that you get better astrometry from Gaia DR3. So is there any obvious reason?
So you're asking like why there's more astrometry using Gaia DR2?
Yeah, yeah.
So basically it was released earlier.
Okay.
So it started to providing data earlier, and once they introduced Gaia DR2 and started using it in their pipelines, sometimes they go some bigger observatories. I see in data that they tried to move on to another one, but they see that staying with the Gaia DR2 for this moment it's at the same level. So but the Pan-STARRS, they moved from Gaia DR2 to early data release of DR3. So we also saw that.
Thank you.
Thank you, Carolina. So I was wondering, when you're showing these sky plots, so for the Catalina, so there's very clear biases on UCAT two, where when you look at above and below the galactic plane with your RA residuals, your declination residuals, it's all to one side. What I was wondering if you have any ideas why that difference between RA and dec, and also just within, say, RA, why the clear biases are positive above the galactic plane, negative below the galactic plane?
Positive, sorry, again, the ending, the positive, why?
Positive above the galactic plane and negative below the galactic plane. So why the difference between the two sides?
I don't know. I don't know the reason for that.
Is it just the problem with the orbital fitting? Is that in modeling or is it that's done for all of them that happen?
I don't think it's the orbital fitting because we can see it, the orbits when we see at the good observatory example as Pansters, we don't see that. So we know that the orbit fitting is working for them. So it's not working just for this specific catalogs, for this specific years, for this specific observatory. So there's something on there. It looks like there's something on their side, but I don't know yet.
Thank you.
Karolina, I have a question about the orbital fitting, and it might be that the orbital magnitude mean that it doesn't affect it at all, but when you see sort of longer term trends in the data, assuming they're there, could that be explained also by drag mechanisms that might be in effect, or I don't know, orbital precession? Do you have to account for those sorts of things, or are you just assuming that the orbits are all closed?
They are close to what?
Well, when you fit, basically, how do you go about fitting an orbit? I mean, I'm interested. What physics do you have to account for?
So there's at this point MPC is using. Sorry, I don't know exactly what's your question. Your question is about like, do I also think there might be a mistake in the orbit, basically?
I mean, how do you do the fitting? Like, what do you have to assume to fit an orbit?
So for the orbit fitting, we are using 6 parameters, and for that, we are using all of the observations that we have. We are using also the most massive planets and a few most massive another objects that are impacting when there's some close approach. There are some relativistic there as well. And for now, for them, we are not using non-gravitational effects because only for a few objects we have confirmed, for example, the Yarkovsky effect. But for the normal, for all of them, we are using this without. So basically, there's a lot of things like that. That it's all in the orbit that is used in MPC. I don't know if that's answering your question.
I think it goes in half. So, like, you don't expect then Yarkovsky to have a dominant effect on the long-term evolution?
For a specific object or for the group?
Either.
It has. We know it does, but most of the time our data is not accurate enough to see it. That's why I said for now we only have like a few hundred confirmed Yarkovsky objects. We also see it in models. For example, there are some families that we see that after the impact, they're like some asteroids from this family that they went to two directions in orbit, and we see that it's coming from the Yarkovsky effect. This is the only explanation. So there's stuff like that. But for this orbit fitting, we are not accounting for that because our data is like not at this level. To do it for all of them, yeah, we have over 1.5 million objects, and again, Yarkovsky detected for like few hundred.
Thank
you very much. This is about the apparent magnitudes. These are not spherical objects, right? And they're internally rotating. So what does it mean when you put up in this diagram apparent magnitude?
So they are not spherical, but basically this is the center of photocenter, basically, of the object.
For a rotating shape of some kind?
That would be amazing, but at this level, no, we don't have models for most of these planetary asteroids. We have 3D shaped models only for a few of them as well. So that would be great to do it. Also because actually we can for some objects and for some very accurate astrometry, for example, coming from Gaia. But now I'm talking about the asteroid astrometry from Gaia, not about the stellar catalog that they provide. We can see that actually the center of the light and center of the mass differs, and we are able to see it in data, but only for this extremely accurate observations from Gaia. But for now, we just basically are fitting to the photocenter because that's the level of the data that we have right now. But I don't mean it doesn't mean that it's bad. I just mean like this effect is very, very small. And yeah.
Thank you.
Thank you.
Any final questions from the room or on Zoom? So with that, let's thank Karolina again. And we'll see you at the end of July. I'll send an email about the date of the next seminar.